What can we do with a Z80 processor? More than 2 years ago I put one on a breadboard and connected it to an Arduino Mega. The Arduino emulated ROM, RAM and a serial I/O device. And so the Z80 could already write Hello World on the Arduino IDE debug terminal. This system was very limited, however. The Arduino could only keep track with a comparably low clock frequency of around 100 kHz, and the memory was limited to the 8K of SRAM offered by the Arduino. So why not putting it on a prototype board together with a 128 KB static RAM and a serial interface chip? This already allowed me to write simple assembly programs and control these with a terminal emulation on my PC. And as I had breathtaking 4 MHz and 64 KB addressable memory from the SRAM chip, there was everything I needed to run the Engine CP/M operating system on it. Trying all these old programs like WordStar, Multiplan, which is the predecessor of today's Microsoft Excel, or some ASCII-based games like Ketchum, which evolved into Pac-Man later, Ladder, later known as Donkey Kong, or a recent port of the Gorilla game for CP/M. Next step was to connect the PATA drive so that the computer could boot from there. In practice I used the compact flash card, as these can also operate as PATA drives. Before, it had to load the operating system files over a serial connection provided by the Arduino each time. In part 6 I then connected a PS2 compatible USB keyboard and made a video card based on the TMS 9918 for it. And this is where the project is now. But there are still some more things to do. Maybe you ask yourself what this lithium cell is for? Well, static RAM can store data retentively if it remains powered with a low voltage. It draws less than a microamp in this case, and so it keeps its data for decades, at least in theory. Because of this, my idea was to use a part of the RAM also as a substitute for a ROM chip. This turned out as rather flaky. The problem is, when powering the computer off or on, some of the pins which are relevant for writing show undefined levels for a few microseconds. But this is long enough to corrupt some of the data, and if this happens to the bootloader, the computer will no longer start. So I went ahead and donated a 32 KB of EEPROM to it. The second improvement I made was about the RAM. I designed a proper bank switching circuit with 4 NOR gates. Bank switching allows applications to access more memory than the 64 KB an 8-bit CPU can address. So on my system the 128 KB of RAM is split into 4 32 KB banks. For the Z80, the green bank is always visible between 8000 and FFFF hex. This is the common bank. The bank switching logic uses 2 of the digital outputs of the DAR chip to determine which of the other 3 banks are mapped to the lower area between 0 and 7 FFF. So I can control per software which one of the 3 RAM banks to use. If both signals are high, which is always the case after power on, the EEPROM is mapped into low memory and the computer can boot from there. So I put the CP/M kernel and the bootloader on the EEPROM. When powering up, the bootloader first copies it to its designated position in common memory and starts it there. Then the EEPROM is replaced by one of the RAM banks. Now CP/M is running completely in 64K of RAM and the EEPROM is no longer needed. With 128K of usable RAM, this DIY computer is already better than most home and personal computers of that era. But over time, the circuit became quite complicated. Soldering 8 ICs, of which one comes in a PLCC package on a small prototype board, is a pain. And digging through thick layers of wires hunting for bugs no less. So it was time to make a proper PCB for this. After creating the layout with KiCad and free routing, I placed my order on the PCBGoGo website. PCB GoGo offers services all around PCBs at a very attractive price. Bring your projects to the next level and order your circuit boards for only $5 or even for free. I ordered the boards for my Z80 computer and the graphic module, and a few days later they arrived. And see what a beauty this is. So stable and reliable. Soldering was done in less than half an hour and it was real fun. After soldering the resistors and the chip sockets, I had to decide which oscillator module to use there. The parts that I already had were rated for 6 MHz, so I decided for a 6 MHz module. With this, the computer will run 50% faster than with the 4 MHz I had in the prototype. The next decision was on which pin header to use. I designed the board so that it can be fitted either with a straight or an angled pin header. With straight headers we can stack modules on top of each other like so. But the distance must be big enough to allow a good air circulation. Some chips can get really hot. However, I decided for angled connectors and a ribbon cable with the female counterparts. This doesn't look that neat though, but so I can unfold the boards and lay them side by side. This makes it easier to probe signals during operation. Now I plug an Arduino Mega, to which I uploaded the loader sketch before, to the right side of the pin header. But then I noticed a small problem which I haven't considered before. Cutting a notch helped me out there, and now the Arduino fits perfectly. I also plug in a USB to serial converter and connect the serial port of the Arduino with the second serial port of my computer. Then I start the terminal emulation on my PC with a speed of 187.5 kilobits per second. This is the clock frequency divided by 32. Before I had a 4 MHz oscillator and the rate was 125 kilobits per second. Then it was time to launch the rocket. For this I crafted a little Windows app based on the Qt framework. Together with a loader sketch on the Arduino, the EEPROM was written in a few seconds and I could see how CP/M boots up on the terminal emulation. When finished, the loader app takes the role of a file server. The dir command shows the files and I can now run my applications like Microsoft Basic, for example. Still, my aim is to get independent from any PC or Arduino. So I wanted to copy the files to a compact flash card. I plugged it in, but after power on, the card released its magic smoke. Very annoying. This was due to a stupid mistake I made in the circuit diagram, and this also showed up on the PCB, of course. The error was fixed and a new card was ordered quickly, but my computer didn't recognize it at all. Digging into it with a logic analyzer, I found out that the read strobe got active before the flash card was actually activated. This tiny delay actually came from the address decoder that determines the chip enable from the I/O request in the I/O address. The PATA standard, however, demands that the read comes in after the card has been activated. The SanDisk card I had before seemed tolerant of this, but the Transcend that replaced it was not and refused to work. So I made another glue logic that brings everything into the right order. And with this I can take the Arduino away and the thing boots from EEPROM and the flash card. So for the future I have to integrate another chip on the circuit board. And it is already quite full. Maybe I'll make an extension card, let's see. Talking about extension cards, I already made a video card that allows to connect the computer to a TV or monitor. Up to 6 modules can be connected at the same time. And I plan more modules for this in the future. So subscribe and stay informed about every new video I publish. As a supporter you can enjoy ad-free previews. Check out the links in the video description.